In section 2.4, we're going to discuss the continuity of a function. The idea of continuity is closely related to the limits that we discussed in sections 2 and 3. So we're going to start by talking about the continuity of a function at a point where x equals a. And then we'll expand it to continuity over an interval and continuity everywhere. But to begin with this continuity at a point, we're going to use an illustration that I think will help us see what's going on and understand the idea. And so this is what we're going to do. Okay, we're going to imagine that we have issued a challenge to several universities across the country to build a bridge over the Etowah River. If you're not familiar, Etowah River is the one that feeds Lake Allatoona here in our local area. And so each team, as they try to accomplish this, they split their teams into 3 groups. The first group we'll call Team West, and their job is to build a bridge that leads up, build a road that leads up to the bridge on the west side of the river. And then Team East will build a bridge that build a road that leads up to the bridge on the east side. And then lastly, the third team, which we'll call Team Bridge, they're in charge of actually building the bridge itself. So we have 2 road teams and a bridge team, and they have to work together to make one seamless road/bridge that goes from the east side of the river, over the river, and off to the east side. So what we're going to do is we're going to look at a handout. If you haven't already seen it, there's a handout posted in the classwork page or classwork tab of Google Classroom. And so we're going to look through that handout together. And on the handout, there are 8 pictures, 8 graphs that illustrate what each team did. And what we want to do is look at each of those graphs and determine, was the team successful in building their bridge and road combinations, or did they fail? And if they failed, what part of the project didn't go correctly? So we want to try to do this in words that are not mathy, right, but words that are related to the project, to the building bridges and roads. So let's turn to the handout. All right, so here we see the first few universities. We have Auburn, number 1, University of Tennessee, and then down a little further we have the University of Georgia and the University of Kentucky. So we'll start with Auburn. Okay, what it looks like here is that Auburn's bridge team built a bridge. Their east and west teams both built roads, but the west road doesn't lead to the bridge and the east road doesn't lead to the bridge. So I don't think we can say that the University of Auburn was successful. Okay, if you're driving towards this bridge from either direction, you're just going to end up falling into the river. So that's not good. Team 2, University of Tennessee, their west team built a road. Their east team built a road. They don't match up, so from both directions you're going to fall in the river. But worse yet, it looks like the bridge team failed to build a bridge entirely. So University of Tennessee has a few problems here. Their roads don't match, and they don't have a bridge. The University of Georgia got a little further. The west team and the east team both built roads, and those roads led to the same point on the river, but for some reason their bridge team doesn't look like they built their bridge in the correct location. So unless you Dukes of Hazzard it over the river, you're not going to be successful in trying to drive from the east side over the bridge into the west side. The University of Kentucky. University of Kentucky's west team, the team on the left there, they did some interesting things. Looks like they built a scenic highway going along the river instead of building a road that actually led to the river. So that's no good. But then also their east team built a road that didn't lead to the bridge. So they have a bridge and they have an east road that leads to the river, but their west team never made it to the river, and their bridge and east side road don't match up. So they have lots of problems as well. Now if we move on to Purdue University, we see that their situation is kind of similar to University of Georgia, except that Purdue didn't bother building a bridge. Okay, their east road and their west road match up, which is, I guess, half good, but their bridge is nowhere to be found. So once again, it's either Dukes of Hazzard or fall into the river. Ohio State University, the Ohio State University, both their east and their west teams built scenic highways on either side of the river, but neither road actually takes you all the way to the river. Plus, I don't see a bridge anywhere. So they failed to build a bridge, and their east and west roads go parallel to the river, and that's no good. All right, number 7, we have UCLA. And UCLA, if you only look at the east team and the bridge team, everything looks pretty good. You could successfully drive from the east onto the bridge, but once you cross the bridge, you're going to get stuck in the mud on the west side because the west side road leads to a completely different spot on the river. So they at least could drive onto the bridge from one side, so they're the closest so far, maybe. But then finally, we have Michigan State University, number 8. It appears that their east and west teams both built roads that led to the same spot on the river, and their bridge team built their bridge in that exact spot. So it would appear that Michigan State University is the only successful university of the 8. So going back to our notes here, what 3 things had to happen in order to have a successful bridge? Well, we had to have the west side road and the east side road both had to meet at the same point. The bridge team had to show up and build a bridge. And lastly, the location of the east and west roads had to be the same spot as the location of the bridge, right? So 3 things. The roads had to meet at the same spot, the bridge had to be built, and the bridge and the roads had to be in the same spot. So we're going to now try to turn this into math terms. Okay, we're going to use some of the limit notation that we've talked about in the previous 2 sections to try to describe this. So the 3 requirements for the bridge we just discussed. Now let's talk about the 3 requirements for a function to be continuous at a point. And the first is analogous to the roads. Okay, we said that the east and west roads had to match up to the same point. Well, that's the same idea as what we discussed in the last couple of classes. Okay, the limit of f of x has to exist as x approaches a. Okay, remember we talked about if the left side and the right side don't agree, like if you're traveling along the left side of the function towards a and you get one value, but as you travel along the right hand side toward a, if you get a different value, if those 2 values aren't the same, then the limit doesn't exist, right? So the left side and the right side have to come together and be coming to the same point as x approaches a. So that's how we know that the limit will exist. Secondly, this is analogous to we have to build a bridge. The function has to be defined at a. Okay, so we have to actually be able to plug a into the function and get a value. And third, analogous to actually having the road and the bridge built in the same spot, we have to have the limit of f of x as x approaches a equal to the value f of a. So now what I'd like for you to do, you may have to pause the video for a minute in order to do this, but I'd like you to go back and look at the 8 graphs from those universities and label which of the 3 requirements here were not met in each picture. Okay, so I'll work through the first one with you. All right, going back to Auburn University, the first issue that we have here is not that f of a is defined, because we see there's a bridge there. So f of a is defined, that's good. But the first requirement, that the limit exists, that requirement is not met. Because if we travel along the function on the left-hand side getting towards f of a, which is where that blue vertical line is, where the river was, as we move towards from left to right along that left side function, we see that the limit is what looks like y equals 2. And as we move along on the right side toward that blue line, it looks like the value is y equals -1. So because from the left we get 2 and from the right we get -1, we have to say that the limit does not exist. So the requirement that's not met for Auburn is the limit does not exist. All right, so see if you can do the other 7. using that math terminology. Okay, the limit does not exist, or the function is not defined, or the limit does not equal the function value. So now that we've defined continuity, we need to talk about what are the things that can make a function not be continuous, or maybe better said, what kinds of discontinuities can we have? In what ways can functions fail to be continuous? Okay, and there are three major types of discontinuity. Okay, the first is called a point discontinuity, or sometimes called a removable discontinuity. In these, the only thing that is wrong is either f of a is undefined. Okay, so the limit exists, but f of a is undefined, or f of a is defined, but the limit does not equal f of a. Okay, either one of those two situations would be a point discontinuity. So we call it a point discontinuity because it's continuous except there's one point. If we could just fill in one point on the graph, then the function would become continuous. All right, but since there's a hole in the graph, we have a point discontinuity. The second type is called a jump discontinuity. Okay, and this is where the limit does not exist because we get one value from the left-hand side and some different value from the right-hand side. Okay, now both of the values are real numbers. So an example on this one would be Auburn University. Again, if we looked at Auburn, the limit from the left was 2, the limit from the right was -1. Two different real number values from the left and from the right make for a jump discontinuity. And it's called that because that's what it looks like. Right? The graph jumps, abruptly from one point to another. The third kind of discontinuity is an infinite discontinuity. And these would be the types of graphs we saw where we had universities that built those scenic highways that paralleled the river. In math terms, what we have is an asymptote. Okay, if the graph has a vertical asymptote, even if it's just on one side, I think the University of Kentucky built a road that was parallel to the river on just one side. That counts as an infinite discontinuity. We call it infinite because the function either goes up towards positive infinity or it goes down to negative infinity on as x approaches a, so on either side of a. So those are the three types of discontinuities, and I would challenge you to go back and look at those 8 graphs again and see if you can identify the ones that we said were not continuous, which was all of them except Michigan State. Just put a little label in there. Did we have a point discontinuity, a jump discontinuity, or an infinite discontinuity at each of those spots? Now, usually at this point in class, if we were doing this lesson in class, I would ask for some volunteers, okay, and I'd have you come up and try to sketch a function that has a point discontinuity, and then I'd have somebody else come up and sketch a jump discontinuity, okay, and so on and so forth. So see if you can, just at your desk, sketch a graph of a point discontinuity, and then sketch a second graph that has a jump discontinuity, and then sketch a third graph that has an infinite discontinuity, and try to make them all different from the graphs that you see on the handout. Okay, they don't have to be a lot different, but just see if you can come up with something that looks different than what we already have, just to give you a little more firm idea in your mind of what each of these discontinuities look like. All right, one of the last things we wanted to be able to do is just look at a graph quickly and decide, is this continuous or not continuous? So you can either discuss amongst yourselves or just come to a conclusion on your own. Is this continuous? Is this not continuous? And if it's not continuous, what kind of discontinuity do we have? Okay, same thing for this graph. Is it continuous, not continuous? And if it's not, what kind of discontinuity is there? All right, so this pretty much brings us to the end. I just want to mention, I said that we would describe continuity on an interval and continuity everywhere. So continuity on an interval is simply a function. We say a function is continuous on an interval if it's continuous at every point inside that interval. So if we looked at this graph for a moment, okay, and we only looked from, let's say, from here to here, okay, so from some negative value of x up to 0, we don't see any jumps or gaps in this part of the graph, right? So this function is continuous on an interval from some spot over here up to 0, all right? It's not continuous at this one point where the dotted line is, but it does appear to be continuous on just about any interval that doesn't contain that one point. Okay, so that would be continuity on an interval. We say that a function is continuous everywhere if it's continuous for every single point on its domain, or for every possible value of x. So this function is clearly not continuous everywhere because we've got this big jump. But many of the functions that we deal with, and most of the functions that you deal with in your high school career leading up to calculus, most of those functions are continuous everywhere. So things like power functions and polynomials, exponential functions, those are all continuous everywhere functions. So if you fully understand the idea of continuity at a point, then it's pretty easy to extend that concept to continuity on an interval and continuity everywhere. So I had intended to also discuss some delta epsilon proofs parallel to this lesson. It's not officially part of section 2.4, but it fits as well here as anywhere. However, I don't want to try to do that via video. It's, I think, just maybe a little bit too complicated, and there would probably be questions as I went along, and in a video I can't stop and answer those questions. So it remains to be seen. I may teach the delta epsilon proofs along with section 5 on Friday, but I may not. We'll see. It kind of depends on how we do on time and how you guys are handling this continuity stuff. So we'll play it by ear. I'm sure you guys won't be too heartbroken if I say we won't do the proofs, but I do think it's valuable. So if we have time, I think we'll try to do it. We'll see. All right, so I hope that makes sense for everybody, and if you have any questions at all, please feel free to email me. I will be back in class on Friday, Lord willing, and I'll see you then. Thanks.